So if I denote by y sine inverse, the derivative of sine inverse is 1 over the square root of 1 minus x squared dx, and all this is dy. So then I have, I didn't mean to write sine, I meant to write y dy. Okay, but now I have to be careful because I need to find the limits of integration. Sine 0 is 0, right? So if I apply arc sine to 0, I get 0. If I apply arc sine to 1/2, I get pi over 6. How come? Because sine 0 is 0 and sine pi over 6 is 1/2. So then final y squared over 2 from 0 to pi over 6. 1/2 can wait outside patiently. I plug in pi over 6 squared. And minus when I plug in 0, I don't have anything. So this is 1/2 pi squared over 36 or pi squared over 72. You can approximate if you want. There is no need. How do we feel about the substitution with definite and indefinite? Should we choose more? You want me to let you choose? There is another one that just caught my eye. Let's see. Any questions on this, on the previous problem? Any questions? Okay, here it is. The integral from 0 to 1 from dx over 1 plus the square root of x to the power 4. I have no idea where this will lead. We'll figure it out together. The function is undefined when the square root of x is -1, but that's not going to happen. So between 0 and 1, the function is continuous. So there are no problems here. So then, any suggestions? I can only think of one thing. I cannot think of anything else. I don't know where this is going to take me, but it's my only chance. So then I'll say that dy equals 1 over 2 the square root of x dx. I'm in a little bit of a pickle here because this is no problem. This is very clear. It's y to the 4th. But I'm having a problem here. The 2 is not a problem, so I can multiply by 2 and divide by 2. So I have the dx over 2, that's okay. But I also have a square root of x here. So I know what to do. We did that before for a few minutes ago. I can solve this equation for the square root of x. So then the square root of x is y minus 1. So this will be replaced by y minus 1. But let's take it easy, slowly. Let's see how we account for everything. 2 is outside because I have dx over 2. Or maybe in this situation, maybe it's even better to solve for dx. I'm solving for dx, this equation. So I have 2, the square root of x dy will equal dx. Maybe that's better just for this situation because it may be confusing. So I'm going to erase the 2. We're going to get back to that 1/2 in a moment. You'll see in a moment. So let me just try it so that everything is clear. So the limits of integration, when x is 0, the lower limit is 1. When x is 1, the upper limit is 2. Okay, so now carefully, let's make sure that we have everything accounted for. The denominator is clear, y to the 4th. dx is 2 times the square root of x, but it will be replaced by this. 2 times the square root of x times dy. I'm not changing the rules on you. When it appears to be slightly more complex, it's better and safer to solve for dx. So we'll take the 2 outside, the integral from 1 to 2. I have y over y to the 4th, which is y to negative 3, minus 1 over y to the 4th, which is y to negative 4, dy. I did this because it's easier to integrate. So I separated into 2 fractions, and I got y over y to the 4th, which is 1 over y to the 3rd, which is this, and then 1 over y to the 4th, which is y to negative 4. It's easier to integrate to find the antiderivative. So y to negative 3 plus 1 over that number minus y to negative 4 plus 1 divided by that number from 1 to 2. I will not plug them in. I will simplify a little bit more. So 2 negative 1 over 2y squared, and this will be plus 1 over 3y cubed from 1 to 2. And now I will plug in. Messy calculations. I can tell you that I had a professor who would never calculate anything till the end. He would say, it's messy from now on, you do it. But I can't do that to my students. I wish I could, I know, but I can't. Okay, 2 squared, 4. Negative 1 over 8 plus 8. 1 over 24 minus. When I plug in 1, there is a minus already, so positive 1/2. But now minus, when I plug in 1, 1/3. I'm checking my numbers. That's correct. 24. I should have a minus, but it changes into plus. I should have a plus, but it changes into minus. That's correct. Okay. So the least common denominator appears to be 24, a 3, a 12, and an 8. Negative 3 plus 1 plus 12 minus 8. 13. And I think it's minus 11 over 12. And I think it's 2 over 12 or 1 over 6. Let me see if I skipped anything or missed anything. I hope not. Negative 3 plus 1 plus 12 minus 8. So this is 13 indeed. This is negative 11. So I got a 2 over 12. I think I'm okay. Any questions?
So could you isolate dx to dy for the problems too?
Oh, that's exactly what we did, but I did a shortcut. Yeah, you can always solve for dx and replace it by this product and then simplify. So in these situations, I would highly recommend do that because it's easier. You can always solve for dx. But here, because of this was in the way, it wasn't clear what to do, how to replace what. So that's why in this situation, I did solve for dx and replace it in here. Because I had the 2, I had the square root of x, which had to be replaced by y minus 1, and then I had dy. And the denominator was clear. So in this case, it was easier to show what I'm doing by solving for dx to plug it in, to replace it. But if it's just a constant or something like that, I don't do that. But it's up to you. You can use any method you like. But you can always solve for dx or whatever the variable is that you are trying to solve for. Do we need other examples? Should we do more? Anyone? Or can I go back? Should we go back to section 5.4? Or we need more of this? Okay, since you're not saying anything, I'm hoping that someone is watching. The last thing that I would like to go back to is what is called the net change theorem. The net change theorem is something we used before a long time ago, but we did not call it this way. This is what we know. This is the fundamental theorem of calculus, but also called, in this case, the net change theorem. And I would like us to look at a couple of examples. So let's suppose we are given the velocity function, v of t, in meters per second, is given for a particle moving along a line. So we're asked to find, so it's given to us as 3t minus 5, 4t between 0 and 3. And we're asked two questions. We're asked to find the displacement, and we're asked to find the distance, the total distance, the distance traveled by the particle. So two different things here. First question, the displacement is the integral. So the integral from v of t dt on the given interval, 0 to 3. The distance traveled, however, is the same thing, but of course the integral from 0 to 3 from the absolute value of v of t dt. So this is the difference. And after this, no more new material. This is the final concept that we need to look at. Okay. So let's find the displacement. So the integral from 0 to 3 from 3t minus 5 dt, which is 3t squared over 2 minus 5t, everything between 0 and 3. Luckily, I don't have to plug in 0. So this is 3 times 9, 27 over 2, minus 15. When I plug in 3, 9 times 3, 27 over 2, minus 15. Least common denominator 2, and this needs a 2, so this is 27 minus 30, and the answer can be negative. However, when we determine the total distance, and we've done that before, the total distance, this is the integral from 0 to 3 from the absolute value of 3t minus 5 dt, which has to be positive. Is the integral of a positive function. This is one of the properties of the definite integral. Before that, remember, we have to dissect this absolute value. And that is 3t minus 5 for 3t minus 5 being positive, or negative 3t plus 5 for 3t minus 5 being negative. We've done this a long time ago. That's one of the applications. That's why we did that. So I have to solve this inequality. So this is, oh, that's not good. Sorry. T greater than or equal to 5/3. And of course, I don't have to solve this ever. If this is greater than or equal to, this is less than 5/3. Okay. So then the integral from the total distance becomes a sum of two integrals. One from 0 to 5/3 from this, and the other one from 5/3 to 3 from this. And that number has to be positive. Because remember, the particle can move in the positive direction, can move in the negative direction. We have to add all those distances, regardless of which direction the particle is moving into. If it's a negative velocity, then it's moving, going backwards, etc., etc. So negative 3t² plus 5t from 0 to 5/3 plus 3t² minus 5t from 5/3. Look at that. But this was 13 to 3. Okay, I plug in. I don't have to plug in 0, luckily. So negative 3/2 times this squared, 25/9 plus 25/3. Okay, now careful when I plug in 3. I get that 27/2 minus 15, that which I got before. But now minus when I plug in 5/3, so this is 3/2 times 25/9, but now plus 25/3. I'm checking my numbers. Negative 3/2, 25/3, correct. 25/3, yes. With 3, yes, 27/2, correct. Minus, oh, yeah, yes, minus 15, that's correct. Minus 3/2, yes, with 5/3 squared. 25/9, yes, and then plus, yes, 25/3. Okay, let's see what this mess is coming out to be. Okay, negative 25/6. Now these two, positive 50/3. So these are all accounted for. Now here. Uh, 27/2 minus 15. And what do I have here? It's minus 25/6. Okay, let's see. This with this, right? Minus 50/6 plus 50/3 plus 27/2 minus 15. Even if I simplify here by 2, I still need the least common denominator to be 6 no matter what. So negative 50. Here I need a 2, here I need a 6, and here I need a 6. No. Here I need a 3, and here I need a 6. One more time. 6, I need a 2, yes, and I need a 3, yes, and I need a 6, yes. So plus 100 plus 81, yes, and minus, is this 90? Yes. Okay, let's see. 100 minus 90 is 10. 10 plus 81 is 91. Minus 50, 41/6. That's the total distance covered by the particle.